Hey there, this is Mr. Wilson, Module 3.5, the expansion. So here it says turn to page 24 in your packet and complete the following problems. But before you guys do that, I wanted to just stop you. And let's just say that we're about to have a party, or maybe you're going to have a party later on this weekend or something like that. What type of people would you want to come to your party? Would it be all ages? Probably not, right? So let's just create like a number line here, and let's talk about the people that you'd want to come to your party. Maybe like the lowest age would be like 15, and then the highest age would maybe be 20 or okay, like maybe 21, but not really 21-year-olds because we don't need those type of people. So we could say going all the way up to 21, but not equaling 21, and actual 15-year-olds can come. Okay? So this represents a graph of an interval from 15 to 21, not including 21. So writing this as an inequality, we've seen this before. We could say that ages of people that are coming to this party have to be less than 21, but bigger than or equal to 15. This is called an inequality. Okay? Pretty basic. Two ways of representing the same information. So we could continue on this path. Another way of communicating this information is this thing that's called set notation, and it looks exactly like this, where it's talking about the ages that are greater than or equal to 15 but less than 21, except you just add these little braces to it, and you put this thing right here and include this. Okay, so what this is saying is all ages such that the ages are in between 15 and 21, not including 21. All right, so that's just a fancy way of writing it. Now the last thing that I wanted to show you is this thing that's called interval notation. An interval notation with the same bit of information just starts at the lowest number all the way up to the highest number, which is 21. And we put a parenthesis on the 21 and we put a bracket on the 15. Now the reason why we put a bracket on the 15 is because the 15, it's equal. And the 21 here, since it's not equal to 21, it has an open circle, that means that it gets a parenthesis. So how about this? If I had x and it was less than 5 but bigger than 3, how would we write this in interval notation? Well, the lowest number is 3, the highest number is 5, and then because it's not equal to 5, it's a parenthesis, and since it's not equal to 3, it's a parenthesis. So how would things change then if I were to put a line underneath this? And so now it could be equal to 3. Well, that 3 would no longer have a parenthesis, but now it would have a bracket. That's how interval notation works. So let's go back here to the beginning of our little PowerPoint. And let's zoom in on the directions on what it's being asked. So there's a couple things, features of these functions that we do understand. One of them being the end behavior. We've talked about that. We also understand intercepts, where it crosses the x-axis and stuff like that. Kind of seen maximum and minimum, and then when it comes to increasing and decreasing, that's where we really haven't seen. And also domain and range, we've mentioned that, but it's not the same thing. So let me kind of digress here and talk about increasing and decreasing functions. So first off, here we see that this graph is going up. Imagine if you're like riding a bike on this, and here you are, okay? And you're riding a bike, and see how you're going up the hill, and then once you get to this point right here, you would then be going down the hill. So we could say that the function is increasing on the intervals of A to B, and then also, see, once you go down this hill, you would then be increasing again. The function is increasing from C to D. Okay, so that's where this function is increasing. So notice that we're just looking at the x values. We're not considering the y values. We're just saying that it's going up at this from this time to this time, and also going up from this time and this time. So the function is decreasing on the intervals of B and C. Kind of makes sense? All right, let's put this to the test then. See if you can answer these questions here. When is this graph increasing? When is it decreasing? And when is it constant? It is kind of hard to read, but we see that it's increasing from 0 to at least, I think that's 25. And then it's also increasing from 35 to 40. Okay? So that's the increasing, intervals. Now it's decreasing right here. Imagine like riding your bike down, right? Decreasing from 40 to 50, and then we can say that it's constant from, 25 to 35, and then also 50 to 80. Now the reason why this stops here is because this is talking about weight and a person's age. So obviously, I mean, this doesn't continue on forever. Ages don't continue on forever. They stop roughly around 80. That's the median age. So anyways, you guys kind of understand that? Cool. Let's move on. Okay, so let's now talk about finding the domain and the range from a graph. When you guys hear those words, I know the first thing that comes to your mind possibly is a t-chart. Okay, and we understand that the x values are the domain and the y values are going to be the range. So whenever we use a t-chart, we have a limited amount of x values that we choose, and then remember these are the inputs and we get an output after we input these values. But the reality is when it comes to, like, say, a line, okay, and we graph a line, sure, we only choose a couple points to graph it, but then do you guys see the arrowheads? The arrowheads indicate that the graph continues, or the function continues in either direction. So that means that we would have to create a t-chart that just has every single x value possible for this graph. So instead of creating a t-chart like that, we're going to represent the domain as an interval. So let's go back here. The domain will be kind of like the dimension of the width, and the range will be the dimension, the height of this particular function. So let's say that this is 3 and this is 5. We would say that the domain goes from 3 to 5, and that's how we'd represent the width of this particular function f of x. Okay, and then the range, since it goes, we could say that this is, say, 6 and this is 13. We would say that the range goes, and we say the lowest number first all the way up to the highest. So it starts at 6 and goes all the way up to 13. That would be the domain and the range for this particular example. So let's try one. Here we've got a function that's x to the 2/3. I know it looks weird, but we could still kind of figure out what the domain and the range are. Remember, this is like captured from a calculator, so this is continuing on. So we could put like arrowheads right here. But go ahead and see if you can figure out the domain and range. Alright, so since the x values are continuing going this way, since this has an arrowhead, almost like I could put like a arrowhead and just say, alright, this is continuing going this way, we see that those x values are going all the way to, well, negative infinity. So how do we represent that? Infinity isn't an exact number, so we always put parentheses for infinities. So this is negative infinity. And then over on this side, this is also going to be continuing this direction. So we say that the x values, or the width of this function, is going from negative infinity to positive infinity. That's the domain. Another way of representing that is you could say all real numbers, or use this symbol that's like a funky looking R. Okay? Now the range does not go all the way down to negative infinity. Notice that it stops right here. What is that value? Yeah, 0. So the lowest value that it starts at, basically, for the height is at 0. And then where are these values going to go as this goes out in both directions? Are we going to reach just to 10, or do you think it's going to go past 10? Yeah, it'll probably go past 10, right? All the way up to infinity. So we'll say infinity, and then don't forget that the infinities get parentheses. So that would be the domain and the range of that function. So let's go back to our little worksheet that we had, those questions 1 through 6, and let's just look at problem number 5. So if we look at this problem right here, we can figure out the intervals on which the function is increasing and decreasing. So why don't you guys try that first? Where is the function increasing and where is it decreasing? All right, so again, you want to consider like this is like a bike trek or something like that. We see that if we were on our bike going this way, even though the arrow is pointing up this direction, we read the graphs from left to right. So we would be decreasing right here. So this arrow is pointing up this way, so that's from negative infinity all the way to this x value right here, which is negative 2. Bracket. Okay, and then it's also decreasing from right here all the way down to this point right here. So we could say that from 0 all the way to 3, it is also decreasing. Okay, now do you guys see how I put a point right here? This is called a maximum and this is called a minimum. Now the reason why these are important aspects of this function is because this is increasing, increasing, and then right at this point, this maximum, we are no longer going in the upward direction, but now we are going in a downward direction. Okay, so it's like a vertice. It's like that weightlessness as you jump in the air and you kind of float for a second, or maybe less than a second, and then you start going down. So here this is going down, 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 and then at this point, it is now increasing. Okay, so let's talk about increasing. Where is this function increasing? So from here, negative 2, all the way to 0. And then it's also increasing from 3. And then this arrowhead indicates that it's going all the way to infinity. And the infinities get the parentheses. So that's increasing and decreasing. Okay, now let's talk about domain and range. So what is the width, or what is the domain of this function? And what is the height, what is the range of this function? Alright, so since we have arrowheads going in this direction and this direction, we could say that the domain for this function is all real numbers. Now if you don't like this, you could obviously just put the negative infinity and positive infinity, but this is probably simpler. So anyways, now let's talk about the range. What's the lowest point? Is this going to go all the way down to negative infinity? No, it kind of stops right here, right? So the lowest point is negative 5. And then since we have these arrowheads that are going in the up direction, pointing up, we know that it's going to continue all the way to infinity. Alright, moving right along, let's start this lesson, Module 3.5, the expansion. So notice our objectives today are we're going to identify the degree, the zeros, and the end behavior of each polynomial, and hopefully that'll help us when it comes to graphing it. And then the last thing we're going to be looking at is this thing called binomial expansion, and that's where we use this thing called Pascal's triangle. Some of you have probably heard of this before, and if you haven't, it's alright. I'm going to go over it regardless. So, here, this is beginning with this idea of the fundamental theorem of algebra, which basically states this. Anything that has a degree of whatever, that's how many roots it will have. So let me give you an example of what I'm talking about. So if I have something to the 4th power, okay, then we're going to have up to 4 zeros. Okay, now we also have to consider this thing called multiplicity. Now if you guys know what multiplicity is, then this will come easy, but let me show you an example of what multiplicity looks like. So if we had the factors x plus 1, x minus 2, and x plus 1 equals 0, what would be the solutions here, or what would be the zeros? Remember, we said each of these equal to 0, and that's how we find them. So if I took that x plus 1 and set it equal to 0, we'd subtract 1 from either side, and we get x equals negative 1. Okay, so one of the zeros, or the solutions, is negative 1, and then you know the shortcut. Basically what we're doing is we're just thinking, how would I get this to the other side? That would be 2, and then this one we'd also get negative 1. So now do you guys see how this factor and this factor are the same? So they're going to produce the same 0. This is called multiplicity. Basically, whenever you have the same factor, that'll produce the 1, 0. Okay, that's multiplicity. So even though this is a degree of 3, okay, we should have 3 or up to 3 zeros. We only have 2 in this case because of the multiplicity. Get it? Cool. All right. So this is what we're going to do. We're going to identify a couple things, basically to help us graph this. First off, this question number 1, what is going to be the degree of this polynomial? Yeah, right? So when we distribute this or do the FOIL, we'll get x times x, so that means that this will be a degree of 2. And then the next thing that I want to know is what is the zeros going to be? So if this is plus 1 here as the factor, then that's going to be negative 1 as a 0. And then here, since this is negative 2, that's going to be positive 2. Okay, so those are our x-intercepts. Then from there, I want you to basically come up with the end behavior, and then from there we could put it on the graph. So this is what I mean by that. So we know that it's a degree of 2. Now, is that a disco or is that a touchdown? Good, it's a touchdown. So we know it's going to be like this, and since it's positive, we know it's going to be facing upward. Okay, we know that it's going to cross right here on negative 1 and then positive 2. So we can roughly say that this parabola is going to go like this. Okay? I don't know how low it's going to go. I don't know whatever. I just know that it's going to kind of have this this look to it. Okay, it's going to cross right here, and then I know that it's going to be going up as we go to the right and going up as we go to the left. So how do I describe this end behavior as we go to the right and to the left? Good. So as x approaches negative infinity, the function is increasing, and as x approaches positive infinity, the function is increasing. Okay, and we can clearly see that from the actual graph. So why don't you guys try these two and see if you can come up with what is the degree of the polynomial, what are the zeros, and then what is the end behavior, and then see if that will help you get a general idea of what the graph would look like. All right, so this one's kind of tricky because we think, all right, well, this has a degree of 2. Well, it does if we just had this, but since we have an x on the outside, we know that that will be a degree of 3. Now, when it comes to the zeros, we don't have to do anything. We don't have to distribute. We're just going to leave it just like this, and we're going to set each of these equal to 0. If you set x equal to 0, you're just going to get a 0. And then if you set this equal to 0, you take the square root, okay, and then you'd subtract the 1, so we know that our zeros are going to be negative 1 and 0. And then lastly, since this is a degree of 3, we know that this will be a disco, and so that we'll have end behavior as we go to negative infinity, it's going to go down, and as it goes to positive infinity, it's going to be going up. So it'll look something like this. The next one has a degree of 4, we could see because that's 2 and that's 2. So degree of 4. And then our zeros, see, this is when we're going to have a situation of multiplicity. So we're going to have negative 1 and positive 2. And then our end behavior is going to be similar to the first one. I know you guys can't see it right here, but it's as x approaches negative infinity, it's going up. And then as x approaches positive infinity, it's also going up. Okay, so you got that? All right, so let's just recap real quick. This one right here, what do you think this will have? Let's just communicate this orally, okay? This has a degree of 1, okay? And the zeros, well, if you just set this equal to 0, you'd subtract the 1 over, so the 0 is at negative 1. And then since it has a degree of 1, that's going to be a disco, and it's a linear function that looks like this, right? And then here, this one looks a lot similar to this one, except now you took that binomial and you squared it. So now that has a degree of 2, and the x-intercepts are still the same, but now the end behavior is a little bit different because it's now increasing as we go to the left instead of decreasing. And then this last example here, it has a cube. So it's same type of thing, but then notice what it looks like. We still have the x-intercept at negative 1. Our end behavior is kind of like what it was here over here because it's an odd function as well, or odd degree. And then this is what the function looks like. What do you guys notice? Okay, obviously it's taking the same binomial and it's just raising it to a higher power. What do you notice about the graphs of these ones? You see that they all have the same x-intercept? And then they all also have the same like y-intercept as well. So just kind of interesting. I wonder what the next degree would also have, right? It would probably include those. So we're going to take these things right here, and we're going to expand them and put them into, basically it's called expanded form. Okay? So this one right here in expanded form just looks like that. Okay, what does this look like in expanded form? Yeah, it's just going to be x plus 1 times x plus 1. And what is this going to be in standard form? It's just going to be x plus 1 times x plus 1, right? Okay, so how do we figure out what this looks like in what's called standard form? Wouldn't we have to take this thing and we'd have to distribute? So that'd be x squared, and then this times this, that'd be plus 1x. This would be plus 1x. This would be plus 1. and then you combine the like terms here, so we have x squared plus 2x plus 1. Cool, we know how to do that. But what would this one look like in standard form? What would we have to do here? Well, we'd have to FOIL this, which we already know, right? That's going to be x squared plus 2x plus 1. But then we have to take that and distribute it times this. So that means we got to take all of this and multiply it times x, which will be x cubed plus 2x squared plus 1x. And then we have to multiply everything times 1, which is this, that's going to be x squared plus 2x plus 1. It's kind of a pain in the butt, right? Okay? If you haven't rolled your eyes yet, go ahead and do that now. And then let me like reassure you that there is a faster way of doing this. Are you interested? Okay, if you are interested, then pay attention. Let me see if you guys can pick up on this pattern. If I have this, all right, and then I do this, do you know what's going on? Do you know what I'm doing? How am I getting the next row? Could you come up with this one? Do you see the pattern? Okay, so this is called Pascal's triangle, and there's nothing like really fancy about it. All it really does is just tell us what the coefficients for a binomial raised to a power. This is a binomial raised to the 0 power. This is a binomial raised to the first. This is a binomial raised to the second, binomial raised to the third, binomial raised to the right, and so on and so forth. Okay, so let's look at this one right here because we just had the binomial x plus 1 raised to the third power. Now let me show you how this is going to kind of pan out. Let me just move over a little bit. So I'm going to first do it with just regular variables like a and b. So if we had a plus b and it was raised to the third power, this is how you would basically do it. You would take this 1, this 3, and this all these other guys, and you'd write 1 plus 3 plus 3 plus 1, and these would be the coefficients. And then from there, you would take whatever this is and raise it to that power. So this will be a to the third. And then you would go in descending order from here. So a to the second, then a to the first, then a to the 0. And then you would look at the second term, which is the b, and you would then go in, or you would increase from 0 and up. So you'd go b to the 0, b to the first, b to the second, b to the third. So now let's clean this up a little bit. Let's see what we got. Anything to the 0 power is 1, and then 1 times a to the third will just be a to the third, right? And then here this is, well, that'll just simplify to 3a squared b, and then this will just be 3a b squared, and then a to the 0 will just be 1, and then b to the third power times 1 will just be b to the third power. Okay? That's how you do that. So let's go back and let's use that x plus 1 to the third power and see how we can multiply it. And if you guys are interested in doing this method, it's going to save you some time. Okay? So x plus 1, and then it's to the third power. So I know it has the coefficients 1, 3, 3, and 1. Okay? Now I'm going to take the x and raise it to the power of 3, raise it to the power of 2, raise it to the power of 1, and then I don't have to put it down here because anything to the power of 0 is just going to cancel out, right? And now I'm going to do the 1. What's 1 to the power of anything? Isn't it just going to be 1? So really, we're done here. So this will just be x cubed plus 3x squared plus 3x plus 1. Now, the good news is this, you guys. If this is confusing to you, if this triangle didn't make any sense, you don't have to use it. You could just go back and do the old school method of just multiplying it all out like I was starting to do right here. You guys could just do that. That's fine. Okay, so don't trip out and don't freak out. Just get the answer. Okay? All right, so that's pretty much it. I wanted to go to our classwork and show you how I wanted you to complete this portion. So quickly turn to page 25 and we will continue here. So it says, here's the equation. Tell me what you know about the function. So I want you to roll like this. First, I want you to tell me what is the degree of this polynomial. Here, this one is 2. Okay? And what does that tell us? If the degree is 2, is that going to be a disco or a touchdown? Yeah, it's going to be a touchdown, right? Okay, next I want you to tell me what the zeros are. Here, the zeros, just take the opposite. We're going to have multiplicity. So x will equal 1. Okay, and then since it's a touchdown, as it's going to the left, it's going to be going up. And as it's going to the right, it's also going to be going up. Now, this is the crazy part. I think with this amount of information, you guys can take this to the graph easily. Okay, or at least this is what I want you to do. I want you to try the best with the information that we have to come up with this equation. Okay, so here if I have x equals 1, I know it's going to cross right here where x is 1. And then since it's a happy face parabola, right, I know that it's going to go something like this. Okay, now even though you kind of graphed it, there's something wrong here. Does anybody see it? What's wrong with this picture? Why is my parabola incorrect? I mean, it is going up. That's what we said. It's a touchdown. We know that it's crossing 1. I got it crossing 1, and it's going up in negative direction. All right? Everything's right except one thing. What is it? Does anybody know? Yeah, we've got an issue here. Since we only have one x-intercept, do you guys see how I went down and I crossed the x-axis and then I came up? See, I crossed it over here as well. So the way that we need to correct this graph is that it could only touch the x-axis at one spot. Here, let me move my little arrow, guys. So this is what I want you guys to consider as you're graphing these. Okay, so good luck, and I will see you next time.